Hello everyone. So today I want to give you an update on the cheat sheet because as I announced, so you can think of this as cheat sheet part 2. Um, on GCR I announced that there are some updates, some formulas have been revised, and I need to actually explain why we had to do that. So far, this was actually a developing story. The definitions were given in such a way that you find them easier to grasp and apply, but there are now some gaps which we need to fill. So if I now recap, you know what the meaning of this symbol is. This is the rectangular function. Um, and when you don't have any subscript, this will simply be um, a unit rectangle, yeah. And by unit rectangle, we mean that this will be half and this will be minus half and this will be 1. So the area is 1, right? So unit in the sense that area is 1. By chance, this also has width 1, but that's only a coincidence. So now we need to change this to some other area. So let's say if we want the area to be tau rather than 1, then we would definitely like this width to be tau because we don't want to change the height, and we want this width to be tau. We would like these two endpoints to be at tau by 2 and at minus tau by 2, right? And now you have a width of tau and the area also is tau. But the problem is this, because area, we don't want the area to be 0, or we didn't want the area to be 0 initially. Now, why we did not want this, I'll tell you. If you remember the formula in the cheat sheet, we had this kind of definition that we constructed it from the unit rectangle through time scaling operation. And this time scaling operation has divide by 0. And this actually required us to rule, we required t to be positive, tau to be positive, sorry. Now, what if we want to include 0? Yeah. So, of course, this division, we still have to avoid this division. So we need a formula where when tau is non-zero, this will be valid. But when tau is 0, we want an alternative definition. And that definition can be done without using this formula. So now what should be this value? The question is, what should be this value? What is a sensible value? So now try to make this tau smaller and smaller. So apply tau, the limit, tau approaching 0. So you see what will happen. This point will, these two actually parts will get closer and closer. And basically, in the limit, this rectangular function will simply become a thin line, right? We are not changing the height yet. So ultimately, it will just become a vertical strip with 0 width and with height 1. So we can easily say, of course, you might think that we should simply start write 1 there, but 1 is not the correct answer because 1 would mean that you have a constant 1 everywhere. Yeah, that's not what we need here. We need a value which is only 1 here at 0. Yeah, at time 0. So what we need here is the Everson bracket, right? And that Everson bracket will give us 1 only when this t, right, is 0, right? Do not confuse this requirement of small t equals to 0 with this condition tau equals 0. This condition tau equals 0 means 0 width, and this small t equals 0 means that, yeah, the value will be 1 only at that point, not elsewhere. Yeah, so now our definition is complete. We don't, this is now applicable to all non-negative values of tau. Um, a similar reasoning can be applied to the triangular function, right? The triangular function, the standard one will be like this. Sorry, I'm not actually proud of my drawing skills. So yeah, it will be 1 minus 1, and this is 1, so the area is 1. And when we want the area, this will be our lambda. But if we want the area to be tau, uh, our definition so far was to start with this unit triangle, unit area triangle, and then apply this time scaling operation. And of course, this is only possible when tau was non-zero. And now, for tau is equal to 0, applying similar reasoning, of course, our graph should be like this, that instead of 1, we will need a tau here, and instead of minus 1, we will need a minus tau here. The height will still be 1, so that the area is tau. And if you now apply limit tau approaches 0, this triangle will get thinner and thinner, and ultimately we'll just have a line similar to that, yeah? So we can just pick this whole thing again. So when tau is equal to 0, we can define our triangular function to be the Everson bracket. So you can easily see that as far as tau is equal to 0 is concerned, there is no difference between triangle function and the rectangular function. They both collapse to this vertical thin strip. I mean, yeah. Okay, so far so good. The next thing is more complicated, and that is the definition of the triangular function when we had a skewed triangle. Yeah? So the way skewed triangle was actually framed so far in this course, let me tell you at the outset that that definition is incomplete. Yeah, it was good enough because we gradually developed it, and you even learned how to apply it till sessional 1. But today we will see why that is incomplete, and we need to complete it, and we need to modify a few things about it. But so far, what we learned is that normally you will have a triangle like this, which is symmetrical. But what if you have a skewed triangle, which means that, okay, maybe less of it is here and more of it is here. This is one way in which it can be skewed, right? Or you can have, yeah, more of it on this side and less of it on that side. Yeah, it doesn't matter. So we'll just pick one of them, and you can easily imagine the other. And because we want this center, initially we wanted this to be at 0. So of course you cannot have tau and minus tau, otherwise it will be the symmetrical case. So it means that this tau has been modified in some way, and we introduce a new parameter. So tau will still be there, and tau will still mean the area. So which means that this width of this triangle still has to be tau, not tau, 2 tau. Yeah, because this is a triangle, the height is 1, so we want area tau, and that requires a width of 2 tau. So of course, this has to be um, tau times 1 minus gamma, and this has to be tau times 1 plus gamma, and with a minus sign. Even looking at these formulas suggests that, and this is how gamma enters here, and then you can have this formula. Yeah, you can actually look in the cheat sheet. We constructed the formula, but you see that these expression 1 minus gamma times tau, 1 plus gamma times tau, it's not easy to actually interpret them. I mean, only special cases are easy to understand. So, for example, what is straightforward is there are these three values. When gamma is equal to 0, when gamma is equal to 1, when gamma is equal to minus 1. When gamma is equal to 0, you have this symmetrical case, right? So you have this tau minus tau, no problem. When gamma is equal to 1, what do you have? What do you have? You have this right side collapsing to 0, left side becoming minus tau. So what do you have? You have this thing, minus 2 tau, 0, 1. Yeah. So you still have that width of 2 tau, height of 1, and area of tau. And similarly, when gamma is equal to minus 1, what do you have? You have this left side collapses to 0, and the right side becomes 2 tau. So 2 tau, 0. You see, so apart from these three values, it is not easy to imagine what. Of course, we also know that gamma has to be between minus 1 and 1, but it's not easy from here to imagine what the other values of gamma could. For example, what could gamma is equal to 0.5 mean? Of course, it's possible, but I don't want to explain it in this diagram. This diagram makes it very difficult to explain that. So we need to actually simplify this picture, and the simplification has to get rid of these horrible expressions. So imagine it will be cool if we retain these two values. Yeah? So in the symmetrical case, we have tau here and minus tau here. So what if we require a modification of this diagram so that we have tau here and we have minus tau here? We still need this skewness. It will still be skewed. So we are not removing the skewness. It will be skewed in the same way, but we want the right side to be tau and the left side to be minus tau. And of course, the center cannot be 0 now. Yeah. So now imagine what happens to this. How do you make this right side, yeah, this value? How do you turn that to tau? Remember, what is that? If you expand that, you have 1 times tau is tau minus gamma times tau. So you have to remove this thing, yeah. So you have to actually add gamma tau to that. And similarly, what happens here if you expand this? Minus 1 times tau minus gamma times tau. So you have to add gamma t to this as well, gamma times tau to this as well. So basically what you're doing, you are moving this whole graph to the right. Yeah. So you're applying shift right. So when you shift this to right, 0 will become gamma times tau. This 1 minus gamma times tau will become tau, and minus 1 plus gamma times tau. So you see now see, this graph is much easier to interpret. Why? Because it has width 2 tau, because it's tau and minus tau. 0 will be somewhere here, right? 0 will always be at the center, and this change of slope will happen at gamma tau. And now you can give a meaning to gamma. Gamma is actually the skewness factor. So gamma tells you which way. Yeah. So here in this case, gamma is such that it is to the right. Yeah. So gamma is positive. That's why gamma tau is to the right. So it is the portion of this support which is to the right. Yeah. So I can now imagine a few values, right? So let's say introduce this value 0.5, and here I'll try minus 0.5. So 0.5 would mean that I will still have tau and minus tau here, because that is not changing. Tau and minus tau here, right? And 0 is the center. 0 is the center. We don't want that change of slope to be at 0, because otherwise this tau and minus tau will get complicated. We want that to be simple. 0.5 would mean that it is between 0 and tau. So it is 0.5 times tau. Yeah, this is gamma times tau. So here we will have a change of slope. So you see, you can have that delta now. If it is minus 0.5, it will be between 0 and minus tau. So minus 0.5 tau, the change of slope will be here, and you can easily see that it is skewed to the left. Yeah. Let's change. Maybe I'll now use another color, and let's use another value, 0.75. and here it will be minus 0.75. So now I'm using this. 0.75 means that it will be somewhere here, right? So the change of slope will be there. So now let's see. This will be my diagram. And this is minus 0.75, so it will be between minus 0.5 tau and minus tau here. So the change of slope will be here. So now you can easily see that all those cases are possible. This would never have been easier in the original formulation. So now what we need to do, we need to get back to that diagram and apply that shift to the right. So we'll pick our formula. So now I'm suggesting the formula, the revised version. Uppercase lambda tau comma gamma of t will have our formula. I'll just write the formula before. We know how to write that formula. And in that formula, we will introduce a shift to the right. Shift to the right. By how much amount? By gamma times tau, because we want this. Yeah, we want this 0 to, instead of having a change at 0, we want to change. You see, initially the change of slope was at 0. Now we want that change to be at gamma tau, so which means that we want to shift the whole graph to the right. So now I'll see how we work that out. So I'll now write that formula for you. Tau gamma t equal. Okay. So if you remember, we had one formula multiplying u of t, and one formula was multiplying u of minus t. This was the right side, this was the left side. And here we had actually t gamma, lambda 1 minus gamma times tau, and this was uppercase lambda 1 plus gamma times tau plus. And we don't have a problem, remember, because we define this for tau is equal to 0 as well. So even when gamma is equal to 1 or minus 1, these terms will still be defined as 1 and minus 1. So, but the problem is that it will get multiplied by u of t and u of minus t. And when this is 0, you will have that thin strip, and that thin strip should have a height of 1. Here it multiplies with u of 0. You will see that it will become u of 0. This u of 0 is half, and that half is actually a problem. We don't want that half because that is an unusual value. So what is needed is to actually make this term disappear in that extreme. So when gamma is equal to 1, you don't want this to be non-zero. So you apply that condition. Gamma must be non-unity if you want this term to be non-zero. Similarly, this term is only acceptable when gamma is different from minus 1. So these two conditions will actually filter them. And this makes sure that these two terms don't interact with each other for the extreme cases. Otherwise, they contribute. And now this is your old formula. I mean, old in the sense that, yeah, you still don't have the skewness is still not there. Yeah. Sorry, the skewness is there, but the shift is not there. Sorry. Because gamma is there, so you have the skewness, you have the extreme cases, but there is no shift. We need that shift. So the shift can now be applied easily. The shift can only be applied if you change this t to some dummy variable. Yeah? Remember, we need this small t in our formula. So this small t has to equal. Now, let me introduce some small lambda as a dummy variable. Yeah, minus lambda. And now that lambda, you subtract from that lambda gamma times tau, and that will be your small t. And here you see you're actually shifting the graph to the right by this amount. So now let me show you in the cheat sheet how I have updated it. Actually, I'll now show you all the changes, right? Rectangular pulse, this is the original formula. Unit area, this is the revised formula. When tau is non-zero, you have this time scaling. When tau is zero, you have the inversion bracket. Triangular function, unit area, when you have area tau, time scaling when t is non-zero, when tau is non-zero, and the inversion bracket when tau is zero. And this version now, the skewed version, remember, is this is the left part of the skewed triangle. This is the right part of the skewed triangle. This condition makes sure that the extreme case gamma is equal to 1 is not considered, because that will introduce a half time Dirac delta. We don't want that. This bracket ensures that gamma is equal to -1 is not considered. Other than that, these two terms will add up as the two parts. So actually, if you remember in that diagram, this will give you the left part, and this will give you the right part. Yeah, and in the extreme cases, only one of them is supposed to be there. And this bar with gamma equals, because you see we introduced sorry, lambda is the dummy variable, and that lambda is equal to t minus gamma tau, t minus gamma tau. This is the shift to the right, which was needed to have a tau here and have a minus tau here and have gamma tau here. So I think that's all you need to know for the modification. Now let's get to the sessional exam and see what this means for you. So let's say if you had this revised definition, how will you solve this, right? So now let's say I am interested in this part, this triangle, from here to here. Let's say I want this thing, yeah, this thing. So before we would locate it at zero because we were interested in this change of slope. But now we need to know we will have this as our tau, we will have this as our minus tau, and this will be our zero, yeah. So because of instead of zero we have -1. So for this part I will have my uppercase lambda, the triangular function, and this will be at t plus 1. Yeah, you remember previously it would have been at t, at just t, but now this will be our center. So it's shifted to the left, t plus 1, and then it is tau. So the tau in this case is, what is the width? 0 and minus t. What is the width here? It is 2, yeah. So you will have 2 here, and gamma is actually 1 in this case, yeah. So now let's compare this to our previous answer. You see that alternative, it's actually I picked the alternative. So we had tau, and now we will have tau plus 1. That's the only thing you need to do, right? Sorry, this 2 cannot be 2. This has to be 1, yeah, because this is I just forgot that this is a triangle, and in a triangle you can't just use the width, you have to use the area. So the area is 1. So you see it is literally the same. This thing here, all you need to do is to replace this t with t plus 1, because now you have that shift. And similarly with this one, yeah, similarly with that one, you can have all these cases. So I think the only difference is to remember this shift now, yeah. That was all. Thank you.